Hello there, and welcome to Science for Sleep. I'm really glad you made your way here tonight. Maybe you're already lying down, tucked in under something soft, or just pausing for a few quiet minutes between the moments of the day. Maybe your room is dark, or dim, or lit just enough to see the shapes of your walls. Maybe the window is open and the air is cool. Whatever your setting, I've made this space for you. It's a place you don't need to be anywhere else but here. A pocket of stillness where science can stretch out and wander gently. This isn't a classroom. It's not a lecture. There are no tests, just ideas. Slow, patient ones. And you don't have to hold on to all of them. You're allowed to drift in and out, to fall asleep somewhere in the middle, to wake up with only fragments left and still feel like you learned something. That's kind of the point. Because sometimes the most interesting thoughts are the ones that arrive softly, when we're too relaxed to question them too quickly. Tonight I wanted to talk about something that has puzzled scientists, mathematicians, philosophers, and children alike for a very long time. The idea that the universe might go on forever, and yet also that it might have an edge. At first, those two things don't seem like they should belong together. They almost cancel each other out. How could something that's infinite have any kind of border? Doesn't infinite mean it just keeps going and going and going, without interruption, without edges, without walls or fences or boundaries or limits? It seems like one of those questions that's either too obvious to ask or too impossible to answer. But here we are, asking it anyway. Because asking questions like this is kind of what humans do best, especially at night, when the world slows down enough for those questions to bubble up. So we'll sit with it, you and I. We'll turn it over. Not to force an answer out of it, but to explore what the question is really made of. To understand what we even mean when we say things like infinite, or edge, or the universe. Sometimes just understanding the shape of a question is enough. But before we float too far into all of that, let me ask you something simpler. What time is it where you are? Not because I need to know, but because I think it's a nice way to remind ourselves that space isn't the only thing we're moving through. You're living in a time right now, a little moment in the great stretch of history and future and everything in between, and this moment, your moment, is the only one like it. Right now, as you hear this, the rest of the universe is still doing what it does. Galaxies are turning, stars are forming, comets are swinging through the darkness. But this second, this minute, this little pause in your evening, it's just for you. That's special in a quiet kind of way. If you're already feeling relaxed or curious, or maybe just barely staying awake, I'd love it if you gave this video a gentle like. Maybe even subscribe if sleepy science stories are something you want to keep nearby. I always enjoy hearing where people are listening from. A small town, a busy city, a forest cabin, or just a bedroom with a soft blanket and a dim lamp. If you want to share that in the comments, I'd be grateful. It's like watching a little constellation of listeners light up around the world. It makes the universe feel slightly more connected, just slightly. And I'll say this too, as always. This video is meant for relaxation and curiosity. It's not a substitute for medical advice or treatment, and it won't fix insomnia or anxiety by itself. But maybe it can give your brain something gentle to focus on, something to wander through while your body winds down. That's my hope at least. So let's begin, slowly. No pressure, just thoughts. You're lying there, maybe looking at the ceiling, or maybe just feeling the weight of the bed holding you gently. And maybe, like so many people have over the years, you've wondered what's beyond all this. Not just the walls of your room or the edge of your city, but the real beyond, the kind that lives above the clouds, past the stars, outside of everything, the kind of beyond where telescopes point and never quite reach the end. Maybe you've heard the phrase, the edge of the universe, and imagined it like the edge of a map, the place where the stars just stop, and there's a kind of blankness, or a black wall, or maybe a shimmering curtain. Maybe you've pictured someone flying a spaceship and reaching that edge, like hitting the end of a highway, unsure whether to turn around or push forward. And then someone says the universe is infinite, and that idea evaporates. Infinite means no edge, doesn't it? No stopping point, no boundary, just endlessness. And yet, the thought of infinity is just as strange. It's not something we encounter in daily life. You can imagine a big number, a really big one, bigger than the number of people on Earth, bigger than the number of grains of sand on every beach. But infinity isn't a big number. It's not even a number at all. It's a kind of concept, a direction that never ends, a road with no final exit sign. So how can both of these ideas be true at the same time? How can the universe be infinite and still have an edge? The funny part is, no one really knows for sure, at least not yet. But we've come up with ways to talk about it, to model it, to explore the possibilities. Some of those ways are mathematical, others are philosophical. Some come from astronomy, from real observations and measurements and data gathered by satellites and telescopes. Some are ideas we've tested, and some are still just theories we're trying to understand. But they all orbit the same mystery. What is the universe shaped like, and what does that shape mean for where it ends or doesn't? And when we ask about the edge of the universe, we have to be careful about what we mean. Do we mean the edge of space, the furthest point out you could go if you just kept moving? Or do we mean the edge of time, the beginning or the end of existence itself? Or are we really asking about something even more basic, like whether there's a place where things just stop? A wall, a border, a place where you reach the end of space and can't go any farther? That's where we'll go tonight. Slowly. One thought at a time. We'll talk about shapes. We'll talk about the curvature of space, the expansion of the universe, the meaning of observable horizons, and how our perspective as small, time-bound creatures influences the way we ask these questions. We'll imagine walking in a straight line across an infinite landscape. We'll ask what happens if you never turn, never stop, never run out of ground. Do you ever return to where you started? Do you find a wall? Or do you just keep going forever? But not all at once. We'll take our time, because part of understanding infinity is realizing that it doesn't rush. It doesn't demand that you grasp it quickly. It's patient, like space itself. So wherever you are, however your day has gone, whatever thoughts are still lingering in your head, just let them slow down. You don't have to push them away. Let them be part of the background hum, like static behind the stars. We'll talk now quietly about something very, very big. You can start by picturing a room, a normal room. It has walls, a ceiling, a floor. You can stand in it and touch the boundaries. It's a closed space, defined. You know when you've hit the edge. Now take away the walls, leave just the floor, a flat surface that stretches in every direction. You start walking, straight ahead. No obstacles, no turns. You keep walking, and walking, and walking. You don't tire. Time doesn't pass in the usual way. You're just always moving forward. Eventually you might start to wonder, will you hit something? Will you fall off? Will you reach a wall? Or will the floor just keep going forever? And what if somehow, after an unthinkable amount of time, you find yourself arriving back where you started, without ever turning around? What would that mean? That the floor is looping, that space is curved, that you've been walking on the surface of something without knowing it? Now zoom out. Replace the floor with the universe itself. Replace your steps with the motion of light or gravity or galaxies. What is the shape of that space? Is it flat? Is it curved like a sphere, like a saddle? Is it open-ended? Or does it wrap around in dimensions we can't quite picture? We're getting ahead of ourselves, but only just. Tonight we're not looking for a finish line, we're just walking, talking, asking, and as we do, we'll discover that infinity isn't what we thought, and neither is an edge. Let's imagine the shape of stillness. It might seem like a contradiction. Shapes suggest structure, outlines, edges. Stillness feels like the absence of all of that. No movement, no form shifting into something else. just a moment suspended without change. But if the universe is our setting, and space itself is what we're trying to understand, then stillness has a shape too, even if it's too large to draw, too slow to notice, too quiet to feel. When people think of space, they often picture it as flat. Not flat like a table or a sheet of paper exactly, but flat in the way that lines stay straight and angles behave the way they were taught to in school. If you draw a triangle on a flat surface, its angles always add up to 180 degrees. If you walk in a straight line, you never curve back around. That's flat space, the kind of geometry we're used to, where shapes behave predictably and distance works the way you expect. But space doesn't always behave like that. Not on large scales. Not when you start asking questions about the whole universe. Imagine again that you're walking in a straight line across a vast, featureless landscape. You're careful. You never turn. You keep your eyes fixed ahead, taking step after step. If space is truly flat and infinite, you'll never return to where you started. You'll keep moving forever, passing new territory that never repeats. But if space is curved, even slightly, then something strange might happen. You could walk forever and eventually loop around, coming back from the other side. Not because you turned, but because the space itself curved around behind you. That kind of space has a shape, even if you can't see it from inside. It might not have a center, it might not have an edge, but it still has a geometry, a way that paths behave, a way that movement unfolds over time. The most common metaphor for this is the surface of a sphere, like the skin of a balloon. From where you stand, it feels flat. You can walk in a straight line in any direction, but keep going long enough, and you'll return to your starting point. The surface has no edge, but it's finite. There's only so much area. The horizon always moves with you, but you'll never find a boundary where it ends. And yet, that's just a metaphor. The real universe isn't a two-dimensional surface wrapped around a three-dimensional shape. The universe, as far as we know, has three spatial dimensions: forward and backward, left and right, up and down. If it's curved in a way that's harder to picture, a way that happens in 4 dimensions or more. And that's where our imagination starts to falter. We can describe it mathematically. We can write equations, draw graphs, simulate behaviors on a computer. But we can't hold the shape of the universe in our heads the way we can picture a globe or a map or a circle drawn on paper. Even so, the shape is there. It determines how galaxies drift apart, how light bends around gravity, how the earliest ripples of the cosmos spread out after the Big Bang. The shape of stillness, in this sense, is the background against which all motion happens. We usually don't notice it because we're focused on the things moving within it. The stars, the planets, the expanding galaxies. But just like the surface of a calm lake shapes how ripples travel, space itself influences how everything behaves. So what do we know about that shape? Not much, but more than we used to. Astronomers have measured the cosmic microwave background, the faint glow left over from the early universe. It's not light from stars or galaxies. It's older than that. It's the afterglow of everything cooling down after the Big Bang. And hidden in that glow are tiny fluctuations, tiny patterns that tell us something about the universe's shape. Not directly, not by drawing it out, but by measuring how those patterns spread across the sky. From those measurements, the current evidence suggests that the universe is very close to flat. Not perfectly, not absolutely, but close enough that if it is curved, the curve is too slight for us to detect so far. That might mean space goes on forever in every direction, or it might mean that it curves back on itself so slowly that the loop is bigger than we can observe, and that brings us to an important idea. We don't actually see the whole universe. We see the observable universe, the part from which light has had time to reach us since the beginning. The rest, if there is a rest, lies beyond our reach. Not because it's hidden, but because the light from those places hasn't arrived yet. And it may never arrive. Depending on how fast space is expanding, So when we talk about the shape of the universe, we have to remember that we're talking about the shape of what we can see. Maybe that shape continues, maybe it repeats, maybe it ends. We don't know. But if the observable universe is flat, and if space continues in the same way beyond what we can detect, then it might mean that the whole universe is flat too, and infinite. No boundaries, no edges, just endless space. Or it could mean that we're just looking at a small patch of a much larger shape, like mistaking part of a curve for a straight line because you can't see the whole arc. If that's the case, the universe could still be curved and finite. It could wrap back around in a shape we can't quite grasp. And that leads to another thought. If the universe is curved, and you keep travelling in a straight line, and you eventually come back to where you started, does that mean there's no edge? Does that make it more or less infinite? You've circled back, the space repeated, but you never reached a wall, so in a way that's still edgeless, still unbounded, just not infinite in the way we first imagined. It gets trickier when we ask how to measure any of this. What does it mean to measure the size of space itself, when space is also what defines size? If you're inside the universe, which we are, and you're using space to define space, it's like trying to measure a ruler with itself. You can compare distances within it. You can chart the separation between galaxies, but you can't step outside and look at the shape from above. There is no above. The universe includes everything. There's no external viewpoint, just perspectives from within. That's part of what makes the question so strange. If you're inside something that might be infinite but might not be, and you can't get outside it, how do you even begin to know what shape it has? You can only look around, collect data, and try to piece together the pattern from the inside out. Still, the idea of shape matters, not because we expect to draw it on paper, but because the shape tells us how the universe behaves. If it's positively curved, like the surface of a sphere, then light travels in loops. If it's negatively curved like a saddle, then light diverges, spreading out faster than you'd expect. And if it's flat, then light travels in straight lines, at least straight in the context of the universe's own geometry. In everyday life, we don't notice these distinctions. The scales are too large, the effects are too subtle. But on cosmic scales, they matter. They determine how the universe evolves, how fast it expands, whether it will keep expanding forever or eventually collapse, whether the structure of space allows for parallel lines to stay parallel, or drift apart or bend together. And that structure, that shape, it's always there. Even when everything else seems still, even when galaxies drift apart so slowly we can't feel the change, even when the sky above your house looks exactly the same night after night. The shape of space is the stage on which all those still moments happen. It holds the quiet, it shapes the stillness, and it may also shape the answer to our original question. Because if space has a shape, whether curved or flat or something stranger, that shape might tell us whether there's an edge, or whether the idea of an edge even makes sense. So far there's no evidence of a wall, no sign of a boundary where things stop. But there is evidence of structure, of rules, of geometry. And that geometry may be the key to understanding where we are, and what it means to move through something that doesn't end, and still wonder where it begins. So what do we mean by edge? It sounds like such a simple word. Most of us learned it early on. The edge of the table, the edge of a book, the edge of a cliff. It's where something ends, where one thing stops and something else begins. Usually nothing or air or a fall. Edges are clean and clear, defined by contrast. Inside the lines is the object. Outside is not. We use the idea of edges all the time, often without thinking about it. The edge of the city, the edge of the forest, even the edge of an idea, the point where what we understand blurs into what we don't. We're comfortable with edges because they help us feel oriented. They create boundaries. They separate what's contained from what isn't. But when we ask whether the universe has an edge, we're not talking about something that fits on a table or inside a box. We're asking whether all of existence, all of space and time and matter and light, could somehow have a boundary, and if it does, what would be beyond that boundary? And if it doesn't, how do we make sense of that? It's hard to picture a thing that includes everything and still has an outside, because outside implies something else, something additional. But if the universe contains all space, then there shouldn't be an outside at all. An edge, in that context, would be a line beyond which there is what exactly? Not space, not time, not emptiness, because even emptiness is still space. So what then? A kind of non-place, the absence of having anywhere to go. That's where the familiar meaning of edge starts to fall apart, because in a physical sense, an edge only really exists in relation to what's on the other side of it. A book ends where the air begins, a sidewalk ends where the street starts. But the universe doesn't sit on a background. It's not placed on top of something else. It is the background. It's the space in which other things happen. So when we ask about an edge to the universe, we're really asking one of two things. Either, is there a point past which space doesn't continue, a literal outer limit? Or, is there some fundamental transition, a change in structure, or conditions, or the rules themselves that marks the end of here and the beginning of something other? That second kind of edge is more subtle. It's not a wall or a barrier. It's more like a threshold. You might not see it or feel it, but past a certain distance, the nature of reality could be different. Maybe the physics changes. Maybe the structure of space isn't the same. Maybe there are regions of the universe with different constants, different particles, or different dimensions. There are theories that suggest such things. Some versions of cosmic inflation, the theory that the universe expanded extremely rapidly right after the Big Bang, propose that our observable universe is just one bubble in a much larger multiverse. Each bubble might be a self-contained universe with its own laws. In that case, there might be a kind of edge, not a hard wall, but a boundary between bubbles, or a region of transition. But we don't have evidence for that, not yet. And that raises another point. When people hear the word edge, they often imagine a place you could go, somewhere you could travel to, a location. You reach the end, you look over the side and you see something, or nothing, or maybe you fall. But that assumes space works like a landscape, that it's a fixed terrain you can move across. In reality, space is dynamic. It expands, it curves. It's not a surface laid out on a table, it's part of the system, and your movement through it is shaped by its structure. So let's consider a simpler analogy. Imagine a video game, not the characters on screen, but the code that defines the world. Maybe the game world is a giant square, and if you walk to the edge, you hit an invisible barrier. That's one kind of edge, the hard limit of the system. Nothing exists beyond it, not even in theory. The developers didn't program it. Or maybe the world wraps around. You walk east, and after a long time, you appear back on the west side. That's another kind of edge, a boundary that loops. It's not infinite, but it has no stopping point either. You never hit a wall, you just repeat. Or maybe the game world generates more terrain as you explore, creating new space dynamically. From inside the game it feels infinite. But from outside, from the perspective of the program, it's still limited. It only exists as far as you've gone. Now bring that idea back to our universe. We don't know whether it's a closed system like the first example, or a looping one like the second, or a generative one like the third. But we do know that from our perspective there is no observed barrier. Light comes to us from billions of light years away. Space continues in all directions, at least as far as we can measure. But even our measurements are limited. The speed of light gives us a horizon, a maximum distance we can see, not because there's an edge there, but because light from beyond that point hasn't had time to reach us yet. We call this the observable universe. It's like being in a fog. You can only see so far, but that doesn't mean the world ends at the fog's edge. It just means you can't see past it. Maybe there's more, maybe not. That idea, the observable horizon, is sometimes mistaken for a literal boundary, but it's not. It's just a limit set by time and the speed of light. The universe might extend far beyond it, or it might not. We don't know. But here's the part that often gets missed. If the universe does have an edge, it's not something we could ever reach in a conventional sense, not because it's too far away, but because of how space itself behaves. The universe is expanding, not into anything, just expanding. The space between galaxies is stretching, and the farther away something is, the faster it recedes from us. At a certain distance, a little over 16 billion light years, things move away faster than light, not because they're breaking any rules, but because the space between us and them is expanding so rapidly. That means even if you could travel at light speed, you'd never catch up, you'd never reach those regions. They're forever out of reach. Beyond the cosmic horizon, that's another kind of edge. Not a wall, not a place, but a limit on what can ever be known, ever be touched, ever be influenced. And yet, that limit changes over time. The observable universe grows as light from more distant places arrives. Our horizon expands, the edge shifts. So when you lie back and wonder whether there's an edge to the universe, the answer depends on how you define edge. If you mean a place where space ends, no. We haven't seen anything like that. If you mean a horizon beyond which we can't see, then yes. But it's not a boundary in the usual sense. And if you mean a fundamental change in conditions, a region where the universe transitions into something different, then maybe. But we have no proof yet. Most importantly, the edge isn't something fixed. It's not waiting for you to find it. It's not marked by a sign or a sudden drop-off. It's a concept that changes depending on your frame of reference, your tools, your definitions. It might be more useful to stop thinking about the edge as a location and start thinking of it as a relationship. A relationship between what's known and what's unknown. Between what we can see and what we can't. Between what exists for us and what exists beyond us. That's what makes the question so rich. It's not about finding a wall, it's about understanding what it means to reach a limit and what lies just past the edge of knowing. And as we move forward, we'll turn to one of the most misunderstood ideas of all, infinity. What is it really? How does it differ from the merely large? And can something be infinite and still have no edge? Infinity isn't a number. We use it like one sometimes, in casual conversation, in jokes, in exaggerations. We say something takes forever, that there are infinite possibilities, that the universe is infinitely large. And in those moments, the word usually just means a lot, more than we can count, bigger than we can handle. But in science and mathematics, infinity isn't just a bigger number than all the others. It's something different. It's not part of the counting system. You can't measure it with a ruler or reach it by adding one more and one more and one more again. It's not what you find at the end of a long line of zeros. It's what lies beyond the idea of endings altogether. If you take a calculator and type in a number that's too big for it to display, you might get an error message. But infinity isn't an error. It's a concept, a definition of unboundedness. It's what you get when you say something never stops, never finishes, never runs out. It's not 10 billion, or a Google, or even a Googleplex. Those are still numbers. They have places. They can be written down. Infinity never arrives. It's a direction, not a destination. This is part of why people get tripped up when they hear scientists say the universe might be infinite, because it sounds like it should be measurable. If something is infinite, then surely we should be able to talk about how big it is or how much it contains. But infinity doesn't work like that. You don't measure it, you approach it. You describe the conditions under which something grows without bound. It's not the thing, it's the behavior. In math, you might see a statement like, as x approaches infinity. That doesn't mean x becomes infinity. It means x gets larger and larger without limit. The process is the point. Infinity is never reached. It's what lies at the end of a pattern that has no end, and that's where things start to feel strange. Because in the real world, we don't deal with things that are truly infinite. We have large, we have small, we have fast, we have slow. But we don't have actual infinity. There's nothing you can point to and say, this here is infinite. Even the sky, which feels endless, is full of objects we can count and measure. Even the sea, which seems to stretch forever, has boundaries, depths, limits. So when we talk about the universe being infinite, we're making a statement not about size in the traditional sense, but about structure. We're saying, as far as we can tell, there's no edge, no limit, no sign of stopping. The geometry of space is such that it continues, and continues, and continues again. This doesn't mean the universe contains every possible thing. It doesn't mean that somewhere out there every version of reality plays out. It simply means that space itself, the fabric of the cosmos, might extend without bound. That you could keep moving in a straight line and never come back around, never hit a wall, never find a final star at the edge of creation. But here's where it gets even more subtle. Something can be finite and still have no edge. Think of the surface of a sphere again. It has a total area. You can calculate it, but there's no boundary, no cliff, no end. You can walk in any direction and never fall off. That's a finite surface with no edge. Now imagine that in more dimensions, a universe that wraps around on itself in ways we can't picture. It might be finite in volume but unbounded in experience. You'd never find a border because there isn't one. You just keep going over and over, always forward, never stopping. That's different from an infinite universe, but it feels similar. Both are edgeless. Both let you keep going. But one loops, the other doesn't. And that's why the difference between infinite and edge-free is important. You can have one without the other. Just because there's no edge doesn't mean the universe is infinite. And just because the universe is infinite doesn't mean it contains everything you can imagine. When scientists try to determine whether the universe is infinite, they look at clues, the curvature of space, the way light behaves, the distribution of galaxies, and based on what we see, the universe appears to be either flat or very close to flat. If it's exactly flat and it doesn't loop back on itself, then it probably is infinite. Not because we've measured every corner, but because the geometry implies it never folds back, it just keeps going. But remember, our observations are limited. The observable universe is a sphere around us, about 93 billion light-years across. That number can be misleading. The universe is 13.8 billion years old, but because space itself expands, the edge of what we can see is farther than that. Light has been travelling all that time, and the fabric it's moved through has stretched. Still, that 93 billion light-year span isn't an edge. It's a horizon, a place beyond which light hasn't had time to reach us. What lies beyond it is unknown, and that unknown space might be part of an infinite whole, or it might be a patch in a larger but finite universe. There's no way to know, at least not yet. Some people struggle with the idea of infinity because it feels too big, too abstract. It doesn't behave like things we know, but that's okay. You don't have to visualize it all at once. You can just understand it as a kind of openness, a system without walls, a space where there's always more space. That's enough. And it's worth saying this too. Infinity doesn't mean chaos. It doesn't mean anything can happen, or that everything does happen. It just means there's no upper limit on the extent of the system. It could still be ordered, still follow rules, still evolve. Infinity doesn't erase structure, it just removes the fence. In fact, some infinities are bigger than others. That sounds strange, but in mathematics it's well established. The set of natural numbers, 1, 2, 3 and so on, is infinite. So is the set of real numbers between 0 and 1. But there are more real numbers than natural ones, different kinds of infinity, different sizes of the unbounded. That kind of thinking helps mathematicians reason about sets, limits, and continuity. In physics, it's harder to apply. because we don't just want to know whether the universe is infinite. We want to know what that means for us, for our location, for our future, for the shape of space and time itself. And this leads to something deeper. If the universe is infinite, then the observable part, the bit we can see and measure, is just a small patch, an island in a much vaster ocean. And if that ocean continues without end, then it raises more questions. Are the physical laws the same everywhere? Is matter evenly distributed? Are there parts of space that look nothing like our own? We don't know, but we can guess. Based on what we see, the universe looks remarkably uniform on large scales. That suggests that our patch is not unique, that the rest of the universe, infinite or not, probably follows the same rules. But again, we can't test that, not directly, which means that even though infinity might be part of our model, it remains a placeholder, a way of saying we don't see a boundary and nothing in the equations requires one. That doesn't mean there isn't one, it just means we haven't found it. And this, in a way, brings us back to the idea of edges, because if the universe is infinite, then there's no edge by definition. But if it's finite and unbounded, if it loops, then again, there's no edge. So in either case, we're left with a strange conclusion. The universe might have no edge, whether it's infinite or not. That's the part people tend to miss. The absence of an edge doesn't tell you whether space is infinite, and infinity doesn't guarantee the absence of a boundary. It all depends on the shape, the structure, the geometry. So maybe it's time to stop asking whether the universe is infinite and start asking something more useful. What's the shape of the space we live in? How does it curve? How does it connect? How does it guide motion, light, time? Because those are the questions we can begin to answer, not by looking for walls, but by watching how things move, how galaxies drift, how background radiation spreads, how gravity bends light. If you've ever read or watched anything about space, you've probably heard someone mention a balloon. Not because the universe is made of rubber or floats in the air, but because balloons offer a useful way to picture something that's otherwise hard to imagine. Not perfect, not literal, but helpful, especially when we talk about space expanding. The balloon metaphor usually starts like this. Imagine blowing up a balloon, and on its surface are tiny dots, maybe drawn with a pen. Each dot represents a galaxy. As the balloon inflates, the dots move farther apart. Not because the dots themselves are moving along the surface, but because the surface is stretching. There's more space between the dots, even though they're not travelling across it. This model gives us a way to think about how galaxies in the real universe move apart as space expands. Not because they're flying away from each other like shrapnel, but because the space between them is increasing. The galaxies stay more or less where they are. The distance grows. Now, here's the important part. The balloon's surface represents space, not the air inside, not the balloon as a whole, just the two-dimensional surface. That surface has no edge. You can walk across it in any direction, keep going, and eventually circle back. It's a finite surface, but it doesn't have a boundary. No edge, no wall, just a smooth, continuous surface that curves around. That's what makes the balloon helpful. It shows how something can be finite and edgeless, how you can move through space without ever finding an end, even though the total area is limited. And as the balloon inflates, every point on the surface moves away from every other point. There's no central dot, no origin point on the surface. Every location sees the rest of the balloon expanding away from it. That's the first thing people get wrong about this model. They try to find the centre, but the centre of the balloon's expansion isn't on the surface at all. It's in a higher dimension. It's part of the full three-dimensional space in which the two-dimensional surface exists. From within the surface itself, the expansion looks the same everywhere. There's no special spot, no favoured direction, and that's the second mistake, imagining the expansion as happening into something. When the balloon inflates, its surface grows larger, but the surface doesn't expand into anything from the point of view of a dot living on it. There's no outside in the two-dimensional world. just more surface, more space between things. Now take that concept and imagine it with three-dimensional space, our actual universe. The expansion we observe isn't happening into something else. Space itself is stretching. There's more distance between points over time. The galaxies aren't flying apart through the universe. The universe itself is getting bigger. We don't see this on small scales. Your room doesn't expand. Your planet doesn't grow. The solar system doesn't drift apart. Gravity holds those things together. But on larger scales, or between galaxies, between clusters, the expansion becomes noticeable. The further away an object is, the faster it seems to recede from us. That's not because it's speeding away, but because the fabric of space between us is expanding. So the balloon helps, but it's still just a metaphor. Our universe isn't the surface of a balloon. It has 3 spatial dimensions, not 2. And there's no evidence of a higher dimensional space surrounding it. If the universe curves, that curvature happens within itself, not into something else. There's no outer air, no room that space is growing into. People often ask, if the universe is expanding, what is it expanding into? The answer is that it's not expanding into anything. Expansion doesn't require an outside. It just means that distances between points increase over time within the system itself. The concept of outside doesn't apply when space contains everything. It helps to think about coordinates. In a normal room, you can describe a location by saying how far it is from the walls or from a corner. In space, there are no walls, so we use relative positions, how far one thing is from another. When the universe expands, those relative distances increase. The coordinate system stretches, not because anything moves outward, but because the measurement between things changes. That's why the balloon example works best when you think about it as on the surface, not inside it. A creature living on that surface would never see the edge, would never reach the middle, would never run out of space to explore, and if the surface kept inflating, they would see other points moving away from them in every direction. Uniformly, no center, no edge. Now apply that thinking to the universe. We look around and see galaxies moving away from us. The more distant they are, the faster they recede. But if you were in a different galaxy, you'd see the same thing. Everything moving away from you. It's not that your galaxy is special. It's that expansion looks the same everywhere. This is called the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. It looks the same in every direction and from every location. No center, no preferred spot, just a vast expanding space where the rules apply everywhere. That might sound abstract, but it has real consequences. It means that our observations, the light we see from distant galaxies, the patterns in the cosmic microwave background, aren't just local curiosities. They're windows into how space itself behaves, into the geometry that defines expansion. And the geometry, as far as we can tell, is flat, or very close to flat. That doesn't mean the universe is like a table. It means that on large scales, light travels in straight lines. Triangles add up the way you'd expect. The rules of Euclidean space apply, but that doesn't rule out the possibility of curvature. It just means the curvature, if it exists, is too slight to detect right now. The balloon surface is positively curved. A saddle is negatively curved. Our universe appears to be somewhere in between, close enough to flat that we don't see any looping or distortion across billions of light years. Still, that doesn't mean the balloon idea is wrong. It's just one possibility. If the universe is positively curved, then it might be finite and unbounded, like the balloon surface. If it's flat and infinite, then the metaphor breaks down. There's no looping, no return path, just space continuing in every direction. Forever. And here's where the metaphor becomes really helpful again. Because even if the balloon surface doesn't match our universe exactly, it reminds us that edges aren't necessary. You can have a finite space with no edge, or an infinite space with no boundary. The absence of a wall doesn't tell you which is true. It also reminds us that expansion doesn't require an outside. You don't need a larger container. The container is the space itself. And that space can grow, not by adding more stuff, but by stretching the distances within it. So when you think about the universe expanding, try not to picture it as a ball getting bigger in a room. Picture it more like the balloon surface growing from within, in all directions, without needing an outside to grow into. The space itself becomes more spacious. And now we can ask something more specific. If space behaves this way, expanding, stretching, possibly looping, then what does that mean for how it's shaped? Can we classify it, name it, predict how it will behave? Because the next layer of this question isn't just about metaphors, it's about geometry. We've used flat, spherical and saddle-shaped as our tools so far. But the universe has more than shapes. It has a structure, a geometry that defines how things move, how light bends, how gravity pulls. And that geometry gives us clues about what's really going on. We've talked about space stretching, about light travelling through expanding fabric, about balloons and infinity, and how the universe might not need an edge at all. But there's a more technical version of this discussion, one that scientists and cosmologists return to again and again when trying to understand how the universe behaves. The question of its geometry, specifically whether space is flat, open, or closed. These aren't just abstract labels. They're real models that describe how the universe might be shaped on the larger scales. And even though we're used to dealing with curves and angles in everyday life, bending roads, hills, domes, cosmic geometry happens on a very different scale. It's not the curve of a mountain, it's the curve of the universe itself, the way it bends light, sets paths, affects time. Let's start with the one we're most familiar with, flat. When scientists say the universe is flat, they don't mean it's like a sheet of paper stretched across a desk. It's not two-dimensional. It means that it follows the rules of Euclidean geometry, the kind we learn in school. Parallel lines stay parallel. A triangle's angles always add up to 180 degrees. Light travels in straight lines, unless it's bent by gravity from a massive object. In a flat universe, space doesn't curve inward or outward on its own. It can still expand, and it does, but the expansion doesn't come with any natural tendency to loop back on itself or spread out into a saddle shape. It's neutral, balanced. Flat space is infinite unless something else limits it. It keeps going in every direction, and the more you zoom out, the more it continues behaving the same way. Next comes the closed universe. This one curves inward, like the surface of a sphere. Not just a ball in space, but space itself behaving like the surface of a three-dimensional sphere in higher dimensions. This is harder to picture, because we don't live in a space that naturally wraps like that. But the key idea is this. In a closed universe, if you travel far enough in a straight line, you eventually return to where you started. You might never notice the curve, because it's spread out over billions of light years. But it's there, gently guiding paths into loops. This kind of universe is finite. It has a limited total volume, but it has no edge. That might feel counterintuitive at first. How can something be finite and still have no boundary? The answer lies in how space connects back to itself. Like the surface of a planet, you can travel forever without hitting a wall, because you're always moving within a loop. There's no outer space for you to fall into. Everything exists inside the structure. A closed universe also implies certain things about its past and future. For one, it would have started with a big bang just like any other model, but it might eventually stop expanding. Gravity, over enough time and distance, could pull everything back in. The universe would stop growing, reverse course, and collapse. That collapse is sometimes called the Big Crunch. It's not the only possibility, but it's one that follows naturally from a positively curved, closed model. Then there's the third option, open. An open universe curves the opposite way, outward, like a saddle. It's not closed in on itself. It doesn't loop. In this model, parallel lines diverge. A triangle's angles add up to less than 180 degrees. Light travelling through it tends to spread out more over distance. This kind of space is infinite, like the flat model, but it stretches in a different way. It's unbounded, but it also naturally tends to keep expanding forever. In an open universe, there's no danger of collapse. The expansion might slow, but it never fully stops. Galaxies continue drifting apart, stars burn out, matter thins. Over vast timescales, the universe grows colder, emptier, quieter. No big crunch, just a gradual fading into stillness. A slow march toward a state sometimes called heat death. These three models, flat, open, closed, are more than drawings on a whiteboard. They're solutions to Einstein's equations of general relativity. They describe how space behaves under gravity, how mass curves space, how time is influenced by energy. And the shape of the universe isn't chosen at random. It depends on one crucial thing: density. Not just the density of matter, like stars and gas, but the total energy density of the universe, including dark matter, dark energy, radiation, everything. There's a critical threshold. If the universe's actual density is exactly equal to this critical value, space is flat. If the density is higher, space curves inward, a closed universe. If it's lower, it curves outward, an open one. So how do we figure out which it is? We measure. We observe the cosmic microwave background, the faint glow from the early universe, and look at how small fluctuations in that glow are distributed across the sky. The patterns in that light tell us how space bends, not just nearby, but across vast scales. We also look at how galaxies are spread, how distant supernovae fade, how gravity lenses light from behind massive objects. And so far, all of this evidence points to a flat universe. Or at least a universe that's flat enough that we can't tell the difference. If there's curvature, it's slight, too small to measure with current tools. That doesn't mean the universe is perfectly flat or infinite or destined to expand forever. It just means that right now, from where we are, it looks flat. And yet flat doesn't mean simple. A flat universe can still expand. It can still accelerate. It can still be filled with structure, with filaments of galaxies stretching across space, with voids where very little exists. It can still change over time, still produce stars and black holes and planets and light. The flatness just describes the backdrop, the geometry. What happens on top of that depends on the contents, and those contents are strange. Dark energy, for example, makes up the majority of the universe's total energy density. We don't know exactly what it is, but we know it's causing the expansion of the universe to accelerate. That acceleration doesn't change the geometry, but it changes the destiny. A flat universe with enough dark energy will expand forever. Not because it's open, but because the outward push overwhelms gravity's pull. In that case, you get a universe that keeps growing colder, emptier, more stretched out. Galaxies move away from each other faster and faster. Eventually they fade beyond visibility. The night sky dims, stars die out, black holes evaporate over incomprehensible timescales, and what's left is just space, quiet, sparse, still expanding. So when people ask, is the universe flat, open, or closed? The answer, for now, is flat. But that answer comes with uncertainty, with margins of error, with assumptions about dark energy, about inflation, about measurements. The question itself is part of a larger search, a search for the shape of space, the fate of expansion, the true geometry of everything. But one thing is clear: no matter which model you choose, none of them require an edge. Flat space doesn't stop, open space doesn't stop, closed space loops back. But none of them include a boundary, a wall, a place where space just ends. That idea, that space has to stop somewhere, doesn't appear in the models, which brings us back to where we started. When we imagine edges, we're thinking in terms of objects, tables, rooms, maps. But the universe isn't an object inside a large container. It is the container, and whether it's flat, open or closed, it has no outer side. There's no direction you can travel that takes you to the end. Just space, continuing, curved or not. So perhaps instead of asking whether space has an edge, we should be asking what kind of space we live in, what its rules are, what its geometry implies. Because once we know that, we can understand more clearly what it means to move through space, to observe it, to live in it. And now that we've seen how space might curve, inward, outward, or not at all, there's a natural next question to ask. If you can have a space that's finite but still without edges, then how does that work? How can something be boundless and yet not infinite? Earlier we talked about the surface of a balloon, not as a perfect model of the universe, but as a useful way to think about something important, how space can be finite and still have no edge. That idea sounds contradictory the first time you hear it. How can anything be limited in size and yet not have a boundary? How do you finish something without reaching a stopping point? We're used to thinking in terms of edges, of corners, frames, outlines. We like shapes that have borders. A room has walls, a page has margins, a planet has a surface. Even the sea, which feels endless when you look out across it, is actually held by the shape of the Earth. But not everything works that way. Mathematically, it's possible for a space to be both finite and unbounded. It doesn't stretch on forever, but there's no location where it stops. You can move through it endlessly without falling off or hitting a wall, and yet the space you're moving through contains a limited amount of volume. That's what we mean by boundless but finite. And it turns out that kind of space isn't just possible, it might actually describe the shape of our universe. To see how that works, start with a circle, a perfect one, drawn on a flat surface. The line itself has a length, a circumference. You can measure it. But it doesn't have an endpoint. If you start anywhere on the circle and move forward, you'll eventually return to your starting point without ever stopping or changing direction. There's no edge, just the loop. That's a one-dimensional example. Now go one step up. Imagine the surface of a sphere, like the Earth. Not the whole ball, just the outer shell. That surface is two-dimensional. You can move north-south and east-west, but you're always stuck to the surface. Again, it has a finite area, but it has no boundary. You can fly around the Earth as many times as you like, and you'll never find an edge. There isn't one. Now take one more step, a three-dimensional version of this idea, a space that's the three-dimensional equivalent of a sphere's surface. It curves back on itself in every direction, but it's not sitting inside a larger container. It's self-contained, complete. You can travel through it in any direction, indefinitely, and eventually return to where you started, just like flying around the globe. That's what a finite, unbounded universe could be. A shape where the total volume is limited. There's only so much space, but there's no outer wall, no final coordinate, no last galaxy. Just more space, connecting back around. No edge, no beyond. Everything is included. Of course, this isn't something we can visualize directly. Our brains aren't built to picture higher dimensional shapes. We can draw analogies, look at slices, imagine surfaces, but the full shape of a finite three-dimensional curved space is abstract. That doesn't make it less real, just harder to draw. And in physics, the reality of a shape isn't judged by whether we can picture it. It's judged by whether it explains what we see, the way light bends, the way galaxies spread, the way background radiation patterns appear across the sky. All of that gives us hints about the underlying shape of space. The possibility of a finite but unbounded universe is one of those hints, because we don't see a wall, we don't see repeated patterns that would suggest a small closed loop, but we also don't see any evidence that the universe has to go on forever. The math allows for a space that curves gently back on itself, large enough that the loop is too big for us to detect, but still finite in total size. And here's where things get interesting. A boundless but finite universe, behaves in many ways like an infinite one. You can travel endlessly in a straight line. You never run out of room. You never see a boundary. From your point of view, space just keeps going, but it doesn't. Not in the strictest sense. It returns, it closes, it connects. If this sounds like it overlaps with the balloon analogy again, it does. The balloon's surface is boundless and finite. So is the globe. So is a torus, a donut shape which you can imagine as a flat rectangle where opposite edges connect. Walk off the right side, you appear on the left. Go off the top, you come back from the bottom. No edge, just connection. Now imagine that kind of connection happening in 3 dimensions. No wall, just a continuity of space. That's a topological idea, not just about curvature, but about how space is stitched together, and that stitching doesn't require an outside. It's not folded up in a higher space, it just is the space. This has implications for how we think about travel, about light, about the history of the universe itself. In a boundless but finite universe, a beam of light could, in theory, circle back around. If the universe was small enough, you might see an image of a galaxy not once, but twice. Once directly, and once coming from the other side. We've looked for signs like that, repeated structures, mirrored patterns, but so far we haven't found any. That doesn't rule out the idea. It just means that if the universe does loop, it does so on a scale larger than what we can currently observe. The loop might be hundreds of billions of light years across, maybe more, and so, from our perspective, it might as well be infinite. That's the subtle part. Our tools are limited, our view is small compared to the total structure. What feels boundless to us could still be finite, and what feels endless might eventually reveal a return path, a route through curved space that brings you back home. But you'd never feel it. Not the loop, not the edge, not the connection. The journey would take longer than the age of the universe. The loop is real, but unreachable. That's the difference between what's true and what's observable, between what a model allows and what we can ever test. Still, even that possibility changes how we think about edges, because the presence or absence of a boundary isn't tied to size, it's tied to structure, to the way space bends and how it connects with itself. You can build a video game world that's infinite. New terrain is generated as you explore, but you can also build one that loops. Walk far enough and you're back where you began. From inside the game, both can feel the same. You never see a wall. You never hit a limit. But one is infinite, the other isn't. So when people say the universe is expanding and ask what it's expanding into, or whether it has an edge, or whether it's infinite, those questions all come back to this. How space behaves when you move through it. Whether it loops, whether it curves, whether it connects. And none of that depends on having a wall. You don't need one. Not to be finite, not to be complete, not even to be infinite. You just need a geometry, a structure, a way for space to work. Or, if space had an edge, where would it be? You could start the question another way. You could ask, how far do you have to go to reach the end of the universe? What would you find when you got there? Is it a place, a boundary, a limit you can cross? The problem is, the question is built on the way we experience the world around us, where things have containers, and containers have ends. You walk to the edge of a forest, you sail to the edge of a lake, you reach the edge of a city and find open land. But in each of those cases, you're moving from something into something else. You're transitioning from one defined region into another that's either emptier or just different. So it's tempting to ask the same thing about space. But space doesn't sit inside something larger. It isn't placed on top of a platform. It doesn't exist within a larger arena that holds it in place. As far as we know, space is everything. All positions, all directions, all coordinates. If there's an edge, it wouldn't be like the border of a field or the rim of a cup. It wouldn't be a place you could walk to or fly to or even point at. But let's play with the idea anyway. Suppose we take the fastest traveller we know, a photon, a particle of light, and we launch it in a straight line with nothing to stop it. It moves at the speed of light, never slows down, never looks back. It doesn't get tired, it doesn't wander, it just goes. Where does it go? From our point of view, that photon moves through expanding space. It covers distance, but that distance is changing as it travels. The space between points stretches, so even though it's moving at light speed, the destination it's moving toward is also moving away. Not because it's fleeing, but because space itself is growing. In that kind of universe, the photon might never catch up to certain regions. They're too far, expanding too fast. Even light can't close the gap. So there are places in the universe that are forever out of reach. Not just for us, but for anything. Ever. That's called the cosmic event horizon. It's not a wall, it's a limit. One that's defined by the expansion of space itself. So already we have one kind of edge, a practical one. A boundary on what can be touched or influenced, even in principle. But it's not a place. It's not a fixed location. It's a distance that depends on how fast the universe is growing and how long it's been doing it. That distance is currently estimated to be around 16 billion light years away from us. Past that, anything we do now won't ever affect what happens there. Not in 1 trillion years. Not ever. But again, that's not the edge of space. It's just the edge of interaction. Beyond that horizon, space continues. Galaxies exist. Light travels. Stars burn. But from here, those events are permanently disconnected. They belong to a region of space we'll never reach. If you followed that photon, it wouldn't hit a wall. It wouldn't bounce back. It would just keep going, always moving into new space, never repeating, never circling back, unless the universe loops, which we don't currently see evidence for. So where is the edge? If you asked that photon, it wouldn't have an answer. From its point of view, if you could say a photon has a point of view, everything is always here. At light speed, time doesn't pass, distance doesn't stretch. The entire journey is collapsed into a single moment. There's no past, no future, no path. Just transmission. But for us, watching from slower frames of reference, the photon's path stretches across time. It shows us that space has no obstacle, no ending, just more space. And if we zoom out, not in space, but in scale, we start to realize that the edge, if it exists at all, wouldn't look like a feature. It wouldn't be marked. You wouldn't see it ahead, growing larger. It wouldn't even reflect light, because there'd be nothing on the other side to illuminate it. It might not even make sense to call it an edge, because edges divide things, one side and the other. But if there's no other side, then what is the edge dividing? It would be the end of space, but beyond that would be not space, not emptiness, just the absence of dimension. And our language doesn't handle that well. We want to say it's nothing, but we imagine nothing as a kind of thing, a blank canvas, a black void, a room with the lights turned off. But real nothing, the absence of space, time, matter and structure, isn't like that. It's not dark, it's not empty, it's not anywhere. Because where needs space to exist? So asking, where would the edge be, becomes a strange kind of question. It pushes against the limits of how we think. Some people imagine that if you travelled far enough you'd find a kind of membrane, a border between space and not space. But what would hold it up? What would it be made of? What's beyond it? If it's a physical thing, then it exists within space, and that means it's not an edge, just another structure. If it isn't physical, then how would you even approach it? Others suggest the universe might just end, the way a game map ends, a cliff into nothing, a sudden absence. But again, how would that work in real space? What would keep atoms from drifting past that point? What would stop light from continuing? Physics as we understand it doesn't support a sudden end like that. There's no reason for space to terminate at an invisible line. And so, gradually the question shifts from where would the edge be, to does the concept even make sense? And from there to something more useful. What does space do? How does it behave? Where can signals reach? What's observable? What's testable? That's the edge we can talk about. The edge of the observable universe. The distance light has travelled since the Big Bang given the expansion of space. That distance defines our current cosmic horizon, the largest sphere around us from which we've received information. About 46 billion light years in every direction. That's not how far we can travel. It's how far light has travelled to us. Beyond that sphere, space continues, almost certainly, but we can't see it. Not yet. Maybe not ever. That's a kind of edge too, not a physical barrier, just a limit on what we know. A soft boundary made of time and light. A border we didn't build but live inside. And it raises another question. If we can't reach the edge, and we can't see past it, how do we know if space continues? Is it just an assumption? Is it based on patterns? We'll come back to that. For now, it's enough to say that the edge, if it exists, doesn't behave the way we expect edges to behave. It's not a place, not a barrier, not a transition. It's something more abstract, or maybe not there at all. Space expands, not like a balloon popping or a wave crashing or an object moving across the floor, not suddenly, not violently, just steadily, quietly, relentlessly. The expansion of space isn't about motion through space. It's about space itself becoming more spacious. It's a stretching, not a scattering. A change in the scale of the universe, not in the position of objects within a fixed container. This expansion began about 13.8 billion years ago. Not from a point in space, but from a state in which the universe was hot, dense, and, as far as we can tell, nearly uniform everywhere. There was no centre, no starting spot. The expansion happened everywhere at once. Every point in space began moving apart from every other point. And it hasn't stopped. It's easy to imagine that expansion is something that eventually runs out, like a rubber band that stretches and then relaxes, or a ball thrown upward that eventually slows and falls. But that's not how space behaves, not by itself, because the expansion of space isn't about momentum, it's about the dynamics of the fabric itself, shaped by mass, energy, and the rules of general relativity. And the strange thing is, over time, that expansion has not slowed down, it's sped up. That discovery came in the late 1990s. Astronomers studying distant supernovae noticed that those explosions appeared dimmer than expected. Not just far away, farther away than they should be based on the known expansion rate. The only explanation that fit the data was that the rate of expansion had increased. The universe was stretching faster than before. That led to the idea of dark energy, a form of energy built into the vacuum of space itself, not a gas, not a force, just a property, something that causes space to expand faster over time, not slower. It's not that galaxies are being pushed apart by some force between them, it's that the space between them stretches. And the more space there is, the more dark energy there is, and the more stretching occurs. It's self-reinforcing. More space means more expansion. More expansion means more space. This creates a universe where expansion never slows, where the distances between galaxies grow ever faster, where eventually most galaxies will drift so far apart that they vanish from view. Not because they're hidden, but because their light will never reach us. The expansion will carry them beyond the cosmic event horizon. In that kind of universe, the expansion doesn't stop. It doesn't hit a balance point. It accelerates indefinitely. The scale of space continues to increase, even if locally, here in our galaxy, in our cluster, things feel calm and stable. It's worth saying again, this expansion is not something you feel. Not on human scales. The Earth doesn't grow. The solar system doesn't drift apart. The Milky Way isn't stretching. Local gravity holds those things together. Expansion only wins on very large scales, where there's enough space between things for the effect to matter. But when it does matter, it dominates. Over billions of light years, space expands significantly. Over cosmic time, it changes everything, and it creates a universe where edge becomes meaningless. Because even if you tried to reach some distant location, to travel at the speed of a light toward the furthest galaxy you can see, that galaxy would keep moving away. The space between you and it would continue to grow, and eventually that gap would widen faster than light can cross it. That's not breaking the rules of physics. It's not moving through space faster than light. It's the stretching of space itself. The coordinate grid gets larger, the ruler gets longer, and you can't run faster than the ruler can stretch. This has consequences. Galaxies that are currently visible to us, galaxies we can observe today, will one day disappear from view, not by fading, but by slipping past the horizon. The light they emit from that point on will never reach us, ever. Not because we're not looking, but because there's no longer a path through space that leads from them to us. Eventually, only the galaxies gravitationally bound to our own, the local group, will remain visible. Everything else will drift out of range, carried by expansion into silence. Future astronomers, billions of years from now, may look into the sky and see only darkness beyond their cluster. No hint of the wider universe, no cosmic background glow, just isolation. That's not science fiction. That's physics. That's what happens when expansion doesn't stop. But it also means something else. That if the universe does have an edge, some final point beyond which space ceases to exist, we will never reach it. We'll never see it. Not because it's far away, but because the path to it stretches faster than anything can travel. That's why cosmologists don't think in terms of reaching the edge. The edge, if it exists, is inaccessible, not just practically, but in principle. It lies outside the realm of what can ever be known, outside the causal structure of our universe, and that's assuming there is an edge at all. So when people say space is expanding, what they often imagine is an explosion, matter rushing outward into nothing. But the reality is quieter, stranger, more stable, but more permanent. Space expands because that's what it does. Because the energy built into its very structure causes it to grow. Because on large scales, that growth accelerates, because there's no counterforce large enough to slow it down. This expansion is not temporary. It's not something we're waiting to finish. It is the state of the universe, and it may be the permanent one. There's still debate. We don't know exactly what dark energy is, or how it might evolve. It could change over time, it could fade, it could reverse. But based on what we see, that's not what's happening now. Right now, the expansion goes on. It carries galaxies away. It carries light away. It carries the edge of the observable universe ever outward. And it means that some parts of space, though real, are already lost to us. Not because we didn't look, but because we looked too late. So when we ask whether the universe has an edge, we also have to ask whether we'd ever notice one, even if it did. Would we recognize it? Would we see it approaching? Or would the expansion carry it away faster than we can ever reach? That's part of the mystery. The observable universe is not the whole universe. It's just the part we can see, the part from which light has had time to reach us since the beginning. A sphere centered on us, not because we're special, but because that's how light works. Every observer, everywhere, lives at the center of their own observable universe. Each of those spheres stretches outward about 46 billion light years in every direction, shaped by the time it takes light to travel and the way space itself has expanded. But beyond that limit, beyond that shimmering edge of visibility, space doesn't stop. There's no sign that anything unusual happens at that boundary. No shift in structure, no change in laws, just distance, just delay, just the silence of light that hasn't had enough time. So what lies beyond? The first answer is simple, even if it's incomplete. More universe, more galaxies, more space, more time, There's no indication that the structure of the cosmos suddenly ends at our horizon. Everything we can see suggests that the patterns continue. These same density fluctuations, the same cosmic background radiation, the same spread of galaxies. Uniform, isotropic, flat. We assume that the universe goes on past what we can observe, because stopping at our current boundary would be arbitrary. There's no physical marker there, no edge in the equations, and no reason for the rest of space to be different just because its light hasn't reached us yet. But assumption is not the same as proof. We don't know what lies beyond. We can't measure it. We can only infer. So our models, even the ones that say the universe is infinite, are still built on what's visible. And what's visible is a small part of the whole. If the universe is infinite, then the observable region is a tiny patch, a drop in an ocean of space. Not because it's small, but because infinity dwarfs anything you can measure. If you zoom out far enough, our entire cosmic horizon becomes a point, a pinprick in a sea of galaxies. But if the universe is finite, if it loops, or folds, or wraps, then it might be larger than the observable universe, but still limited in total size. In that case, we're still seeing just a portion, still missing the rest, still guessing. So the question isn't just what lies beyond the observable, it's how much is there beyond the observable? And even more deeply, can we ever know anything about it? In practice, probably not. There's no signal that travels faster than light, no telescope that can see through time, no shortcut through space. What lies beyond the observable horizon is causally disconnected from us, not temporarily, not practically, fundamentally. That part of the universe exists outside our light cone. It cannot affect us. We cannot affect it. That sounds isolating. But it's true for every point in space. Every galaxy, every star, every planet sees its own slice of the universe. Some slices overlap, others never will. That's how cosmic distance works when space is expanding. You don't need an edge to be confined, you just need time. Now imagine this. There are galaxies whose light we will never see, not because they don't exist, but because they're too far, moving away too fast. Even if we waited forever, their light wouldn't reach us. They're not hidden, they're unreachable. And if new galaxies formed out there tomorrow, if stars were born, if life emerged, if civilizations lit the skies with signals, none of that would ever reach us. Not because we're blind, but because we're late. That's the nature of cosmic isolation. It's not a failure of technology. It's a feature of space-time itself. Still, we can learn a little, indirectly. By studying what we can see, by measuring the background radiation, by charting galaxies, by understanding how structure forms and how matter moves. All of that helps us infer the likely conditions in regions we'll never observe. And what we've learned is this: the universe, beyond what we can see, likely looks a lot like what we can see. Not identical, but consistent. Large-scale homogeneity, smoothness, structure. That's the simplest interpretation of the data, and it's the basis for many of our models. But there's no law that says it has to be that way. The universe could be strange just beyond our view. It could bend, twist, break. It could end or change or fracture into other regions with other rules. We wouldn't know. We couldn't. And that's part of what makes this so difficult. We're used to thinking that anything real can eventually be seen, that everything has evidence, that enough time and study will reveal the truth. But the observable universe is a reminder that there are limits. Not just practical ones, but built-in ones. There are things we will never see, not because we haven't looked, but because they're outside of what seeing allows. Even so, we ask, we model, we wonder. Could there be other pockets of space beyond our own? Regions where inflation stopped at different times, where the laws of physics came out slightly differently, where even the number of dimensions is not the same? That's the idea behind the multiverse. Not just many universes in a poetic sense, but actual disconnected regions of space-time, each with their own properties, each expanding independently. If inflation happened the way some theories suggest, then such regions might exist. They might even be infinite in number. But we can't test that. Not directly. Those other regions, if they exist, are permanently separated from us by space that expands too quickly to cross. They lie beyond the observable, not just in space, but in causality. So what lies beyond? Possibly everything, possibly nothing, possibly more of the same. What we know is this: space doesn't end where we stop seeing. The edge of the observable universe is not the edge of the universe, it's just the limit of what light has told us. The cosmos continues, and in doing so it reminds us of something quiet and strange, that our position, no matter how far we look, is always surrounded by more, not just in distance, but in mystery. In most things we encounter, there's a centre, a midpoint, a location you can name as the origin, a room has a middle, a circle has a centre, a city has a downtown, even a tree has a trunk from which branches spread. So when we hear that the universe began with the Big Bang, it's natural to picture an explosion in space, a burst from a point, with galaxies flying outward like sparks from a firework. And if there's an explosion, then there must be a centre, a place where it happened. But that picture is wrong, not because it's too dramatic or too simple, but because it puts the universe inside something, a larger space, a bigger frame. The actual Big Bang wasn't an explosion in space, it was an expansion of space, a change not in the arrangement of matter, but in the fabric that holds it. There's no centre because space itself was created in that event. Not filled, created. The universe didn't expand into anything, it just expanded. Every point in space moved apart from every other point, not because they were pushed, but because the space between them grew. And that growth happened everywhere, all at once. There was no origin spot, no special direction, just uniform expansion. The same rules applied across all regions, and still do. That's why every observer, no matter where they are in the universe, sees themselves as being at the centre of the expansion. From Earth, we see galaxies moving away from us in all directions, but from a distant galaxy it looks the same. All other galaxies appear to recede from them. No location is privileged. The expansion looks the same from every vantage point. This is one of the stranger truths of cosmology, that every point in space is, in a sense, the centre of its own observable universe. Not because we are each surrounded by space, but because we are each surrounded by the light from space, limited by time and distance. The illusion of a centre comes from how we see, from how light arrives, from the fact that all our observations are made from a single location. Here, Earth, our instruments look outward, our data comes in from all directions, and so, naturally, we build maps with ourselves at the centre. But those maps are just perspectives. They're not about where we are in the universe, only about where we are relative to the things we can see. If we were on another planet in another galaxy, billions of light years away, our maps would look the same. Still centred on us. Still filled with galaxies retreating into distance. Still shaped by time and light. So the centre is a viewpoint, not a place. This isn't easy to internalise. Most of what we experience in daily life is based on fixed positions, up and down, left and right, near and far. A ball thrown from one side of the room to the other has a clear path. A clock ticks forward in one direction. Space has structure. Time has flow. But on cosmic scales, those ideas break down. Direction becomes relative. Movement becomes expansion. Time becomes a coordinate, not a river. There's no up in space, no wall to push against, no axis to measure from, just distance, and how that distance changes. So when we ask where the Big Bang happened, or where the universe is centred, we're asking questions that don't apply. The Big Bang happened everywhere. It's not a point in space, it's a moment in time, a moment when space began to change. And because space itself has no edge, the idea of a centre loses meaning. You can't measure from the middle if there's no boundary to measure toward. A loop has no start. A sphere has no special point on its surface. Every location is as central as any other. Even the idea of before the Big Bang may be meaningless. Because time, like space, began in that moment. There wasn't a ticking clock that led up to it. Time is part of the universe, not something outside it. Of course, there are models that try to go further, that propose earlier states, cycles, bounces, collisions, but all of them work from the same principle, that our universe has no absolute centre. That space is not expanding from a location, but within itself. That the structure is homogeneous, the same everywhere, and isotropic, the same in every direction. These aren't just guesses, they're supported by observations. The cosmic microwave background, for example, the faint afterglow of the early universe, looks nearly identical in all directions. No central hotspot, no directional bias, just a smooth pattern, gently rippled, evenly spread. That uniformity is part of what inflation theory explains. The idea that in its earliest moments, the universe expanded faster than the speed of light, smoothing out irregularities and stretching space so that everything looks the same no matter where you are. But that same smoothing also makes it harder to answer deeper questions. If everything looks the same, how do you know what lies beyond? If there's no centre, how do you define shape? If the universe has no boundary, what gives it form? Those are questions of geometry and topology, of structure and connection. They don't rely on centres, they rely on relationships. How distances behave, how lines curve, how space joins back on itself or reaches out forever. And that's where our earlier questions return. Can space loop? Can it stretch infinitely? Can it end without ending? To answer them, we have to give up the need for a centre. We have to stop imagining a place where it all began, or a location we can point to and say, this is the origin. Because in the largest picture there isn't one. There's only space and time and the rules that describe how they change. What's surprising, or maybe comforting, is that you don't need a centre to feel grounded. You don't need to be at the middle of the universe to matter. Everything we observe is still real. Every measurement still counts. Every galaxy still moves. Every atom still follows the laws of physics. The centre isn't where you are. It's just how you see. And when you let go of that idea, when you stop trying to find the central point, the rest of the picture becomes clearer. The expansion makes more sense. The shape of space opens up. The questions shift. Not where did the universe begin, but how. Not where does it end, but does it. Not where are we in relation to the whole, but what is the whole and how does it behave? And that brings us to a different kind of question. If there's no centre and no edge and space goes on in all directions, then what is infinity in this context? Not as an idea, not as a number, but as something you could move through, something you could fall into, not to reach the end, but simply to go on. When you hear the word infinity, it might feel distant, like a math term, something abstract, an idea that belongs to blackboards and symbols, not to real things you can touch or move through. But in cosmology, infinity comes up all the time, not as a guess and not as decoration, but as a possible description of how space works. It shows up in equations, in models, in how we think about distances and directions and the number of things that might exist. It also raises a question that sounds simple but isn't. If space is infinite, what does that really mean? Not in theory, not as a metaphor, but in reality. Try to picture it. You stand still, and in every direction around you, space continues. Not for a while, not until a boundary, but always. No loops, no curves, no return path, just more space, stretching endlessly. That's not the only model of the universe. As we've seen, space might curve, it might fold, it might even loop. But based on current measurements, from cosmic background radiation, from galaxy clustering, From the distribution of matter on large scales, the geometry of the universe appears flat, or so close to flat that any curvature is smaller than we can currently detect. And in a flat universe, with the right topology, space could be infinite. No edge, no end, no total volume, just more space. If that's true, then the observable universe, the part we can see, is only a patch, a finite region inside an unbounded expanse. Our sphere of visibility doesn't mark a special zone. It's just the area lit up by light that's had time to reach us since the Big Bang. But beyond that sphere, the rest of space may go on, without stopping, without repeating, without changing. And that's where the idea of falling into forever starts to matter. Because in an infinite universe, direction is unlimited, distance is unlimited, travel, in principle, is unlimited. You could pick a direction and move in a straight line forever. Not loop, not bounce, not come back, just continue. And no matter how far you go, there would always be more ahead, more galaxies, more voids, more structure. There would be no edge to reach, no sign that you're getting closer to anything final, just more. This doesn't mean you'd actually see infinity. Your vision would still be limited by light, by time, by the expansion of space, but the space itself, the coordinate grid, would stretch on endlessly. It also means that, in an infinite universe, the number of galaxies is uncountable, not because they're too numerous to list, but because the total is unbounded. You could never write them all down, never map them all. There would always be more. Same for stars, same for planets, same for regions where conditions might be right for life. That's where things become even more unusual, because in an infinite space, with finite types of matter, and finite ways particles can arrange themselves, certain patterns must repeat, not necessarily in the same order, or near each other, or on scales we can imagine, but mathematically, the combinations of particles and energy are limited. Given enough distance, those combinations start to appear again, which means, at least in some models, there may be regions of the universe where matter is arranged just like here, not close by, not in our observable sphere, but somewhere, some unimaginably far place where atoms line up the same way. A planet like this one, a solar system with similar dynamics, maybe even a person reading these same words. That's not science fiction. It's a consequence of applying statistical logic to an infinite space. A reminder that infinity isn't just a number, it's a structure. But we're not meant to think of this as clones or copies, not as destiny or magic, just as the result of unending variation. When the sample size grows without limit, even rare events become inevitable. Given forever, everything that can happen will. Yet none of those repetitions would be reachable, not in a practical sense, not even in a theoretical one. The distances between those regions would be far larger than the lifetime of the universe, far beyond what light could ever cross, even if given trillions of years. So they remain part of the model, not part of the map. Still, this version of forever, the kind that comes from flatness and expansion, helps shape how we see space. Not as a bounded area, but as a direction. Not as a thing with sides, but as a process that keeps going. And in that picture, you don't fall into infinity, you move through it. Any direction you choose, any distance you travel, leads only to more. No signposts, no special regions, no curvature to bring you back, just motion. Of course, gravity still matters. You can't actually drift forever in a straight line without encountering mass, galaxies, clusters, walls of matter strung across the cosmos. But the point remains, space itself provides no limit. If you could go on, you'd never reach the end. In that sense, infinity is not a place. It's the absence of limit, and it's not just about size, it's about implication. Because if the universe is infinite, then many of our usual ways of thinking, about total energy or average density or ultimate boundaries, need adjusting. There is no total energy in an infinite universe. You can't sum it. There's no average that includes the whole, only samples, no map that charts every region, no survey that completes the set. You're always inside a local view. No matter how far you see, there's more. You never arrive at the full picture. There's no border to step across, no edge to mark completion. That doesn't make the universe unknowable, just never fully known. And if you follow that thought long enough, something shifts. You stop asking how big the universe is, you stop asking what's at the edge, and you start asking how space behaves, how structure forms, how expansion changes. You begin thinking in terms of paths, not destinations, of rules, not limits. Because in infinity, rules matter more than boundaries. The way space curves, the way matter clumps, the way time unfolds, those are the things that shape what's possible, not how far you go. There's an idea that keeps coming back, even after you think you've set it down. A simple question with complex consequences. If you travel far enough in one direction through space, will you eventually return to where you started? It sounds like a question about walking a path, about covering enough distance, making no turns and looping back, like flying around a planet and landing where you took off, without ever changing direction. But in cosmology, that question leads to deeper territory, because it's not really about the path, it's about the shape of space itself. When people ask whether the universe loops, they're asking about topology, not just how space curves locally, but how it connects globally, whether it closes in on itself or goes on without limit, whether there's a repeating pattern behind the scenes, one we haven't yet noticed. We already know that space appears flat on large scales, that triangles drawn between galaxies behave the way Euclidean geometry predicts, that light travels in straight lines, unless bent by gravity, and if the universe is truly flat, then it might be infinite, but it also might be finite, if the topology allows space to loop. The key distinction is between curvature and connection. A flat universe doesn't guarantee that space goes on forever. It just means that locally there's no bending. You can still take a flat surface and fold it, wrap it, stitch it together. Imagine a video game map where walking off one edge brings you back from the opposite side. That world feels infinite when you're inside it, even though it's not. Now imagine doing that in 3 dimensions, a space where the left edge connects to the right, the top to the bottom, the front to the back. There's no center, no outer shell, just a repeating space, finite in volume, boundless in experience. That's a 3 torus, one example of a flat but finite universe. If our universe has that shape, then light could, in theory, travel around it. It could circle space and return to its origin, not by curving, but by moving straight, through a space that folds back on itself. And if that happens, we might see repeated patterns in the sky. The same structures appearing in multiple places, the same patch of cosmic background radiation reflected more than once, like hallways of mirrors that don't reveal the edges of a room, but give you overlapping views of the same scene. Scientists have looked for signs of that repetition. They've studied the cosmic microwave background, that faint glow from the early universe, for clues. If the universe loops on itself, that pattern of ancient light should show echoes. It should match up in specific ways in different parts of the sky. Circles that repeat, angles that align. So far, those signs haven't appeared. The data doesn't show the kind of repetition you'd expect from a small closed topology, but that doesn't mean the universe doesn't loop. It might just mean that the loop, if it exists, is too large to detect. The repeated light hasn't had enough time to circle around. That's the strange part. If the loop is too wide, if the size of the whole universe is larger than the observable part, then the repeated images wouldn't be visible yet, or ever. The loop would exist but remain hidden, not because it's not real, but because light hasn't made the trip. So we're left in a place that's familiar by now, a space where the answer could be yes, and yet unreachable, where a loop might exist, but its evidence lies beyond the horizon. Still, the idea lingers. A universe that loops isn't just elegant, it's strange in ways that are hard to ignore. In a closed, finite space, you could travel in a straight line forever and never leave. The journey would never bring you to an edge, it would never bring you to new space, just a return after an unimaginable distance to where you started. But would you recognize it? In a universe that expands, the loop might take longer than the age of the universe to complete. By the time you returned, the place you began would have changed. Galaxies shift, stars die, light fades. Even the coordinates might stretch so far apart that what returns is unrecognizable. And then there's the matter of a light itself. If photons travel around a looping universe, their paths would intersect. They'd crisscross the sky, creating patterns. The same beam of light might arrive from multiple directions. You could, in theory, see your own galaxy from behind. A mirror view from billions of years ago. It's not just a curiosity, it's a testable idea. And while current observations don't support that level of repetition, the data isn't perfect. We may yet find something subtle, a symmetry we missed, a hidden seam. But even if we don't, the possibility remains open. The loop may be there, too large to detect, too slow to reveal itself, like a wheel turning once every eternity. And if it does loop, what does that mean? It means the universe is finite in volume, but without boundaries. It means the edge we sometimes search for, the line we imagine at the outermost galaxy, doesn't exist. Because in a looping space there is no outermost, there is no beyond, there is only more of the same. It also changes how we think about questions like total mass, total energy, total entropy. In an infinite universe, those values are undefined, always growing, never fixed. In a finite, looping universe, they have limits, not because of constraints, but because of shape. That kind of universe feels more like a system, something whole, something contained not by a wall but by geometry. It doesn't make the universe smaller, just different. But there's another version too, a closed universe, not flat but curved, not a torus but a hypersphere, still without edges, still finite but with positive curvature, the kind that brings all paths back together eventually, like moving along the surface of a globe, only in more dimensions. That version has a different future. In some models it expands for a while, then slows, stops, then begins to contract. A long return journey to the state from which it started. The opposite of expansion, a collapse, a cosmic reversal. Right now, we don't see signs of that. The expansion isn't slowing, it's accelerating, and our best models point toward continued growth, not contraction. But the geometry still matters. The loop, if it exists, still tells us something. Not just about where we are, but about how the whole fits together. And it raises a final question in this part of the path. If the universe doesn't loop, and it doesn't end, and it goes on forever, what surrounds it? It's a hard question to ignore, even if no one knows quite how to answer it. Maybe because it feels like it must have an answer. Even small children ask it. If the universe is everything, then what's outside it? What holds it? What surrounds it? We're used to things being contained. Rooms inside buildings, buildings on streets, streets inside cities. Everything seems to sit inside something else. So when we're told that space is expanding, that it's getting bigger all the time, it's natural to imagine it expanding into something. Like a balloon inflating inside a room, a bubble growing inside a sea. But the universe isn't like that. It's not a thing expanding inside a larger space. It is the space. The balloon analogy helps sometimes, especially when we talk about curved, finite universes. But it has its limits, because it still relies on an outside, and in cosmology there is no outside. Not in any direction, not in any dimension we can meaningfully describe. Space doesn't sit within a container, it is the container. When it expands, it's not filling up an empty void, it's redefining what distance means within itself. So if you were to ask, where is the universe? The answer isn't a coordinate. It isn't in a place. It's not located within a larger volume. It is the totality of locations. Even asking where is space expanding into is a misstep. It sounds right, but it sneaks in an assumption that there's a surrounding realm for it to grow into. But space doesn't expand into pre-existing space. It creates more of itself, more intervals, more separations, more distance. And that's where our thinking starts to stretch, because we don't have much experience with this kind of thing. Everything we build has an edge. Every surface has a front and a back. Every room has walls. But the universe, if current understanding holds, has no outside. You can't step out of it. You can't fly beyond its bounds. You can't look down on it from above. Even if space is finite, even if it loops or closes, it's not sitting inside anything else. Just like the surface of a sphere doesn't need to be drawn inside a box, it defines its own completeness. Some theories do propose additional dimensions, higher spatial directions beyond the ones we experience. And in some models, our universe might be a kind of membrane, a brain, floating inside a higher dimensional space, like a sheet on a clothesline moving through a larger volume. In those models, there is something like an outside, but it's not space as we know it. It's not a place you could travel to. It's not accessible from within. It has different rules, different scales, maybe even different definitions of distance, and that's only if those models are correct, which right now is far from certain. They solve some problems in physics, they introduce others, but none have been confirmed. None make predictions we've yet been able to test. So the best answer we can give today is that there is no outside to the universe, not in the usual sense, not a region, not a realm, not a background, just more universe, or nothing at all. And when we say nothing, we don't mean a black vacuum. We don't mean emptiness. We mean the absence of any concept of space or time, a condition in which there is no where, no direction, no dimension, no possibility of moving or looking or measuring. That kind of nothing can't be travelled to. You can't reach it, because it's not out there, it's not adjacent, it's not past the edge, it's what doesn't exist. This makes a lot of people uncomfortable. It's not satisfying to say, there's nothing outside the universe. Not because it's untrue, but because it feels like dodging the question, as if we're just refusing to imagine something. But the truth is, the imagination needs structure to build from. If you take away all space, and all time, and all content, and all direction, there's nothing left to place a thought into. Nothing to even be outside of. No context, no frame. It's not that there's an invisible wall, it's that the whole idea of a wall doesn't apply. Even the word outside breaks down, because outside only has meaning when there's something to be outside of and somewhere to go. So what does this tell us? It tells us that the universe is self-contained. Whether finite or infinite, it doesn't require a beyond. It isn't held by anything larger. It doesn't expand into the void. It simply expands. It defines its own boundaries, or lack of them. And if that's true, then every question about what lies outside the universe becomes a question about something that doesn't exist. Not because it's hidden, not because it's secret, but because it isn't there. That doesn't mean we stop asking, it just means we refine what we're asking. Instead of what's beyond everything, we ask, how did this structure begin? Instead of where does it sit, we ask, how do its rules arise? Instead of searching for an edge, we try to understand the principles that make space and time emerge in the first place. And those questions, the origin questions, pull us further in. Not out into some imagined beyond, but back toward the beginning, toward whatever condition existed before the expansion began, if there even was a before. Because if space and time had a starting point, then perhaps the idea of outside only makes sense after that point, not before. So what do we do with that? How do we even start to approach it? When we think about edges, we usually imagine places. A fence at the edge of a yard, a shoreline at the edge of the sea, a wall at the end of a hallway. But time too raises the question of edges. Not physical boundaries, but beginnings, endings, the first moment, the final tick. And the question that follows is one of the oldest we've ever asked. Did time have a beginning? And if it did, what came before? It feels like time should stretch endlessly in both directions. After all, we experience it as a line, one we move through without choice or pause, always forward, never back. But what about behind us? Is there a point before which there was no before? In our current understanding of the universe, time does seem to have a starting point. About 13.8 billion years ago. That's when the expansion began, when space as we know it started to grow, when matter formed, when light began to move freely. That moment, the one we call the Big Bang, is often imagined as an explosion, a flash in the dark, a beginning in space. But it's not a blast that happened somewhere. It's a shift in the state of everything. And in that shift, time itself begins. There's no record of time before it, no earlier coordinates, no timeline leading up to it. Not because it's hidden from us, but because, as far as we can tell, it didn't exist. Which brings us to a different kind of edge. Not one you can reach, one you live inside. A boundary at the start of time. But if time has a beginning, what does that mean? What does it mean for something to start when there's no before? This is where the language fails us. We're used to causes and sequences, to reasons and consequences. If something begins, we want to know what made it happen, what set it off, what preceded it. But if time itself begins, then that question dissolves. There is no before the beginning of time, not because it's out of reach, but because before has no meaning without time to hold it. Some physicists think of it like a coordinate system that simply doesn't extend further. You can label time as 0 at the Big Bang and assign numbers after it. Seconds, years, billions of years, but nothing before, not because there's a wall, but because there's no axis beyond that point. Others go further. They wonder whether time is even fundamental, or if it emerges from something deeper. A more basic state where what we call time is just a way to describe change. A way to organize events, but not a thing in itself. There are theories that treat the early universe as timeless, not frozen, but undefined. No clock, no before or after. Just a set of quantum possibilities that eventually settle into a state we recognize as space and time. In those models, the Big Bang isn't a bang at all. It's a transition, a phase change, like ice melting into water but from timelessness into history. In that view, time doesn't begin suddenly. It emerges gradually. It comes into focus as the conditions stabilize, and once it exists, it flows forward, not as a rule, but as a consequence of entropy, of disorder increasing, of the arrow of time aligning with the spread of information. Still other theories look at the possibility of a bounce, a universe that contracts before it expands. In that picture there is a before the Big Bang, but it's not part of our time. It's part of a larger cycle, a rhythm that includes contraction, expansion, and maybe contraction again. Time loops, but space never closes. Even more radically, some ideas suggest that time could be circular, not in the way clocks are circular, but in the way paths on a curved surface eventually return. That after enough time you find yourself not at the end, but back at the beginning. None of these models are proven, but they all try to solve the same riddle. How can something begin when there was no time for it to begin in? In practice, we live only in one direction. We remember the past. We influence the future. The arrow of time feels solid. But on the level of equations, in the laws of physics, time doesn't prefer one direction over another. It works forward and backward just the same. So why do we experience time as a one-way journey? Because of conditions at the beginning. The early universe was highly ordered, low entropy, smooth and hot and dense. And from that condition, disorder began to grow, structures formed, energy spread, stars ignited, galaxies spun, information dispersed, and with that dispersion came the sense of time moving forward, the idea that past becomes memory and future becomes mystery. But if those initial conditions had been different, our perception of time might have been different too. Maybe we wouldn't even notice it passing. Maybe it wouldn't pass at all. Which brings us back to the edge, not as a moment to reach, but as a kind of silence, a space in which time itself waits to be born. It's not a place you can point to, not a wall, not a spark. It's more like the bottom of a well, not empty, but without direction, from which time rises, like water beginning to flow. And once it flows, it changes everything. Events begin to happen. Cause and effect take shape. Particles gain motion. Light gains meaning. Expansion begins. But even that doesn't require a full stop at the start. Some models blur the beginning. They round off the singularity. They soften the edge. Time curves gently into being. No sharp line. No final barrier. Just a limit to how far we can extrapolate back. Beyond that limit, our theories break down. The equations return infinities. The models lose coherence. It's not that there's something to see before time. It's that the question stops applying. And that's not a failure of thought. It's a feature of what time is. A structure we live inside. A frame we carry with us. A thing that began not somewhere, but somehow. So when we say time has no edges, we mean it in a few ways. It may have no before, it may have no final end, and it may not be a line at all, but a shape we don't yet understand. Whatever it is, we're inside it. And if the universe has no outside, and time has no before, then maybe there are other limits to let go of. Limits not of where or when, but of what we imagine reality can be. If time had a beginning, then it's fair to ask whether it might also have an end. Not just for us, not just for planets or stars or galaxies, but for everything. The whole structure, the fabric of space, the flow of time itself. Could it all one day stop? This isn't a new question. People have been asking it for as long as they've asked how the universe began. If it started once, could it stop too? And if so, what does stop even mean? Does time hit a wall? Does space collapse? Or does everything just fade? There are a few ways this could go, depending on what kind of universe we live in. Some ideas come from equations, some from observation. All are attempts to see what lies ahead by looking at the rules that got us here. For a long time, there were three major possibilities for how the universe might end. The first was a big crunch. In this picture, gravity eventually wins. The expansion that began with the Big Bang slows down, stops and reverses. Galaxies start to fall back toward one another. Space contracts. The universe shrinks. Temperature rises. Density increases. And everything that once flew apart comes crashing back together in a final collapse. If this happened, it would be the mirror image of the beginning. Not an explosion outward, but an implosion inward. A universe that reverts to the same kind of state it emerged from. Hot, dense, compact. Maybe even back to a singularity. Or maybe into something new. But that doesn't seem to be our universe. Because expansion isn't slowing. It's accelerating, and that brings us to the second possibility, the big freeze. In this version, the universe just keeps expanding, galaxies move farther apart, stars burn out, matter cools, the energy that holds systems together weakens, and eventually, after long enough, everything goes quiet. Not suddenly, not all at once, but gradually, over trillions of years. Stars will stop forming, the last white dwarfs will cool, black holes will slowly evaporate, particles may decay, and the universe will stretch thinner and colder until nothing much is left to happen. This is the scenario most cosmologists currently think is likely. Based on what we know about dark energy, about the shape of space, about the cosmic background. The universe appears to be headed for an endless, cold future. One where time continues, but less and less takes place. There's no edge, no barrier, just a slow dimming. A future without structure, without activity, without memory. And then there's the third idea, the Big Rip. It's more speculative, but it's built from the same data that led us to dark energy. If the force driving expansion isn't just steady but growing, then eventually it could overpower everything. Not just the pull between galaxies, but the forces inside galaxies, inside stars, inside atoms. In that case, the rate of expansion would keep increasing until even bound systems couldn't hold together. Galaxies would fly apart, solar systems would unbind, planets would split, molecules would tear, even space itself would stretch so violently that nothing could remain connected. It would happen in stages. First, the distant galaxies would vanish, then the structures nearby, then the ones here, each one lost to expansion, until at the final moment nothing remains. This version of the end isn't cold, it's violent, fast, not collapse, but disintegration. But right now, there's no strong evidence that we're heading toward a rip. The data fits better with a steady acceleration. That could change. We might one day refine our understanding of dark energy, find that it's evolving, find that it behaves differently at different scales. But until then, the best guess is still the freeze. A universe that doesn't crash or tear, it just fades. And even that idea is complicated, because in a universe that expands forever, the rate of change slows. Galaxies move apart, but their relative motion becomes less noticeable. Light redshifts into longer and longer wavelengths, eventually stretching beyond detection. Information disperses, entropy increases. It's not that the universe ends, it's that it runs out of things to do. Time continues but becomes irrelevant. When nothing changes anymore, time still exists, but it loses its meaning. There's no new configuration, no new memory, just duration without distinction. But there are other ideas too, that the universe might decay, that the vacuum of space is not in its lowest energy state, that there's a deeper level it could drop to, and if that happened, the change would ripple outward at the speed of light, destroying all structure along the way. That would be sudden, silent, no warning, a vacuum transition, a bubble of new physics expanding into the old. It sounds dramatic, but in physics it's not ruled out. If it happens, we'd never see it coming, because the leading edge of that change would arrive at the same time as its effects. But that's not something we can plan for, or test, or feel. It's a possibility, not a prediction. And in the meantime, the universe continues. Stars form, galaxies evolve, light travels, planets spin. People ask questions like this one, because even if the end is cold or distant or quiet, it hasn't happened yet. And the fact that we're here to think about it means something. It means that we live in a time when stars still burn, when galaxies still shine, when information still flows. And maybe, for a while longer, that's enough. So what if it all ends? Maybe it will, maybe it won't. Maybe the concept itself will change as our understanding deepens. But while we're here, asking these questions, looking out into space, looking back into time, there's something else we always carry with us. A limit, not of the universe, but of our place inside it. Because even if everything goes on, we don't. Even if time stretches forward forever, we're just a short part of it. You don't usually think of it this way, but every day you hold a small piece of infinity, not as a metaphor, not as a poem, just as a fact. Every second that passes is part of a sequence with no known end. Every distance you measure, from the floor to the ceiling, from one street to the next, sits within a scale that can divide forever. You don't need to travel across galaxies to touch the infinite. It's already here, built into the way things are. Think about a simple line. Just a pencil stroke across paper. It has length. It has shape. But in mathematics, that line can be subdivided endlessly. No matter how many times you cut it in half, there's always another half to cut, always another midpoint to find. You never reach the smallest point. You never stop dividing. It's the same with time. Between any two moments, there's another, and another. The ticking of a clock isn't time itself. It's just a way to mark intervals. Time, as far as we know, doesn't come in chunks. It flows, not in steps, but in continuity. Space and time, in all their vastness, show up in the smallest things, the quietest motions, the most ordinary measurements, the length of a table, the path of a ball, the second it takes to blink. Each one sits inside a continuum that has no bottom, no minimum, no final unit. That's why infinity isn't just an idea. It's part of the fabric we live in. You might never travel across an infinite universe, but when you pick up a ruler, you're already using a scale that never stops. When you check the time, you're already moving inside a framework with no hard edge. You're part of a structure that extends in every direction, both outward and inward. And even though we talk about infinity as something distant, something in the far reaches of space, most of the time we deal with it in close quarters. A single grain of sand contains more atoms than you could count in a lifetime. A small cube of air contains trillions of moving particles. Every breath, every step, every glance depends on interactions happening at scales too small to see and too numerous to list. We carry those numbers around without thinking. We live inside them. The infinite isn't an abstract ocean. It's the sea we're already swimming in. Even when we talk about finite things, we rely on the infinite to describe them. A finite volume is made of continuous points. A short time is made of infinitely many instants. A simple shape is built from endless relationships between curves and lines. You can't measure a square without invoking an unending grid. You can't measure a second without using a clock that splits time finer and finer. Every tool we use to define the world pulls from the infinite, because that's how reality seems to be built. And it's not just in science, it's in thought. The mind can imagine spaces it will never reach, distances it will never travel, quantities it will never count. The moment you understand that numbers keep going, 2, 3, 10, 100, a million and onward, you've stepped into the infinite, not by proof, just by seeing that the path never ends. Children learn this early. They ask what comes after the biggest number. They try to name it, to contain it. But part of the lesson is that you can't. There's always another, always more. It's the same with space. You can zoom in forever. A cell, a molecule, an atom, a quark. And even beyond that, there are models of structure that go deeper. We haven't hit the bottom. We don't know if there is one. In physics, some theories suggest a minimum scale, the Planck length, beyond which space and time lose their usual meaning. But that's not the same as an edge. It's a limit to what current theory can describe, not necessarily a boundary in reality itself. And if there is no true minimum, no fundamental pixel to space, then the infinite remains. Not just out there in the stars, but right here on the desk, in the shape of your hand, in the grain of the floor. That's not a mystical idea. It's just the way numbers work, the way math describes space, the way physics uses that math to measure the world. When you draw a circle, you're using p, a number that goes on forever. When you calculate speed, you're dividing distance by time, both continuous, both infinite in resolution. When you use a phone, send a signal, light a screen, you're tapping into processes that operate on scales too fine to enumerate. All of this means that the infinite isn't far away. You don't need to imagine the edges of the cosmos to find it. You're already touching it. Every coordinate you plot, every second that passes, every line you draw contains more than you could ever count, more than you could ever stop. And that does something strange. It reverses the usual question. Instead of asking how far away the infinite is, you start to wonder how anything could ever be finite, how anything could ever be fully known, or fully measured, or fully described, if it sits inside this boundless frame. Maybe that's why we keep returning to the big questions. not just because we want to understand the whole universe, but because we see its shape reflected in the small things, the infinity of space in the space between your hands, the infinity of time in the pause between thoughts, the infinity of possibilities in the way one question always leads to another. It's not something we see all at once. It's not something we can hold, but it's there all the same, in every moment, in every place, in every number we can't quite finish writing down. And when you see that clearly, when you recognize that you're already surrounded by the infinite, the rest of the questions don't feel quite so distant. You don't have to find the edge of the universe to wonder what kind of thing it really is. You just have to look at how space behaves, how patterns emerge, how rules apply, even across impossible scales. Because at some point the universe stops being a place and starts being a structure. It's easy to picture the universe as a kind of machine, a physical system with moving parts, space, matter, energy, time, all operating according to rules, inputs and outputs, causes and effects, a giant engine that's been running since the beginning. That picture makes sense. It's helped build our understanding of physics. But it also leaves something out, because when you start pulling at the deepest threads, when you look not just at what exists, but at why things exist the way they do, the universe starts to look less like a machine and more like something else entirely. It starts to look like a thought, not a poetic idea, not a feeling, a structure, one that behaves more like a system of logic than a physical object, one where relationships matter more than ingredients, one where information, pattern, and rules seem to be the real foundation, and everything else emerges from there. That doesn't mean the universe is an illusion, or that it's not real. It just means that, at the bottom, reality might not be made of stuff. It might be made of structure. Take mathematics. No one invented the rules of arithmetic. We discovered them. The way numbers relate to each other, the way shapes behave, the way equations balance. These things were true before we wrote them down, before we noticed them. They're not inventions. They're properties, descriptions of something deeper. Now, look at physics. The more we understand about the universe, the more its behavior seems to align with those mathematical structures. Not just approximately, but precisely. Not just for convenience, but fundamentally. The same equations that describe gravity also describe motion. The same symmetries that govern particles also govern forces. Everything seems to obey patterns, not just loosely, but rigorously. That's not coincidence. It's a clue. It suggests that the universe isn't just a place where matter moves. It's a system where relationships rule, where everything that happens follows from a kind of internal logic. In that view, the universe isn't made of objects. It's made of interactions, of conditions, of rules. And rules, no matter how complex, don't need to exist in space. They just need to be defined. They can be expressed, carried, modelled. They're information, not matter. Which leads to the idea that what we call the universe might just be one particular unfolding of a structure that exists outside of any location. Not in a mystical way, not in a metaphorical way, in a literal one. The universe might be what it looks like when a certain set of rules runs its course, a certain configuration of logic expressing itself as time, space, particles and laws. A thought, not because it's imaginary, but because it follows from a framework, a defined system playing out every consequence it contains. Some physicists call this the mathematical universe hypothesis. The idea that reality isn't described by math. It is math. That every possible mathematical structure exists, but we happen to live in one that can support complexity, stability, and life. Others talk about the universe as information, that what we see as particles and fields are just encoded relationships. Bits. Not the kind you find in computers, but more fundamental, yes or no statements about the state of things. Every interaction, every change, every connection encoded in a web of logic. From that perspective, matter is a kind of expression, not a thing, but a configuration, a result of how the rules interact with themselves. Even space-time under some theories might not be basic, it might be emergent, a property that arises when information is processed in a particular way. Like temperature in a gas, you don't need a temperature to exist at the level of a single atom, but once you get enough atoms together, moving and colliding, the pattern becomes measurable. Space-time might be like that, a pattern that shows up when enough information interacts, a large-scale effect of many tiny rules playing out at once. This is more than speculation. It's where a lot of physics is now pointed. From quantum mechanics to general relativity to attempts at unifying the two, the frontier is filled with ideas about structure and logic, not substance. And the strange part is that this view, while abstract, still makes predictions, still produces models that can be tested, still leads to outcomes we can observe. So the universe might be a system that acts like a thought, not because it's imaginary, but because the framework it follows is closer to mathematics than to mechanics. And because once those rules are defined, everything else just unfolds. It doesn't require intention. It doesn't require a thinker. A thought doesn't need a brain. It just needs structure, a pattern that plays itself out in time. And that brings the idea full circle. Because when you look around, when you see how galaxies move, how particles behave, how light travels, how atoms bond, everything seems to follow from something deeper. Not just forces, but principles. Not just causes, but definitions. This doesn't remove mystery. It makes the mystery sharper, more exact. If the universe is a thought, then it's one we're still inside of, one we're still discovering. And the fact that we can discover it, that we can write equations, build models, make predictions, and watch them come true, is a sign that we're part of that structure too. Not separate from the logic, inside it. The universe isn't something we stand next to. It's something we extend from. You don't have to believe the whole world is an idea, but the more we learn, the more it seems like the world is shaped by something we can describe using logic, precision, and information. And when you accept that, even just as a possibility, you start to see questions like, where does it end, and what's outside it, a little differently. Because if the universe is a system, then maybe it doesn't need an outside. Maybe it's complete in itself. Not because it includes everything, but because it defines its own frame. And if that's true, then maybe the edges we look for, the ones we keep chasing in space and time, are really just reflections of the questions we ask. Even after you've heard that the universe might have no edge, the feeling doesn't always go away. You still find yourself looking for a boundary, wondering how far it goes, trying to picture what's beyond the last galaxy, the last photon, the last possible place. It's not just curiosity, it's something built into the way we think, a kind of expectation that things must stop, that everything eventually has a limit. But maybe the edge we keep trying to find isn't really out there. Maybe it's something we carry with us, something that shapes the way we think about the world and about ourselves. Most of what we experience is local. We walk around rooms, we drive between towns, we measure time in hours and days. Our senses operate in ranges, our tools are finite, our attention is selective. So even though we talk about infinity and unbounded space and limitless time, our minds are tuned for limits. We plan, we divide, we label. We look for edges because it helps us function. It tells us where one thing ends and another begins. But when we try to apply that same framework to the universe, it starts to break down. Space doesn't have a clear border. Time doesn't have a marked finish. The models we use to describe the larger structures don't stop at the last star. They keep going and going and still going. That's hard to internalize. Not because it's too big, but because it's too unlike what we usually deal with. You can walk to the edge of a table. You can reach the end of a book. You can finish a sentence. And somewhere deep inside, it feels like everything should follow that pattern. That even the universe should come to a stop somewhere, somehow. A place where you could say, this is the end. But the more we look, the more that idea doesn't hold up. Still, we return to it. Not because we lack information, but because of how we're built. The human mind looks for patterns, for divisions. It draws lines, not just on maps, but in thought, between inside and outside, known and unknown, self and world. It's not wrong to do that. It's necessary. Every question needs a frame. Every explanation needs a context. But that same habit makes it hard to accept certain answers, especially ones that don't fit the categories we expect. When scientists say space might be infinite, they don't mean it as a metaphor. They mean it as a physical possibility. The structure may have no boundary. The topology may never close. The distance may never run out. But when you hear that, it doesn't always settle. You still look for the wall. You still try to imagine what happens after the last star. Not because you doubt the science, but because the shape of the question remains in your thinking. You're still holding the edge. Even if the edge doesn't exist, that's the edge we carry. It shows up in other places too, in how we think about time. We ask what came before the Big Bang, even if the answer is that time itself began there. We ask what lies outside the universe, even if outside has no meaning in that context. Those questions aren't failures. They're part of the process. We ask from where we stand, and where we stand is always somewhere inside. A perspective, a position, a point of view. Even in science, every observation starts with a frame, a clock, a ruler, a detector. We see only from where we are. And that's why some of these questions persist. Not because the answers aren't clear, but because we can't help asking them from a limited position. We know what the data says, but we still want to picture it in our own terms. There's nothing wrong with that. In fact, it's useful. It's how theories evolve. It's how ideas sharpen. We push against what doesn't make sense until the shape becomes clearer. But it also helps to notice when we're bringing the edge with us. When we ask, how big is the universe, and expect a number. When we ask, what's beyond it, and expect a location. When we ask, when did time begin, and expect a moment before it. These are good questions. They're just framed by limits that might not exist. And that's worth noticing, not to change the question, but to see where it comes from. Sometimes the thing we're looking for, the border, the ending, the edge, isn't part of the structure. It's part of the lens. This doesn't mean the universe is unknowable. It just means that knowing it may require adjusting the frame, letting go of certain assumptions, accepting that some boundaries are useful here but not there. It's not about rejecting thought, it's about refining it. Because when you do that, new paths open. The question becomes less about where the universe ends and more about how its parts connect. Less about before and after, and more about how time arises. Less about boundaries, and more about structure. And in that shift, something else happens. The need for an edge starts to fade. Not because you've answered it, but because you've stepped past it. The shape of the question changes. The need for a final stop becomes less urgent. What you're left with isn't certainty, but something closer to clarity. Not about where you are in the universe, but how you relate to the questions you ask. And when you see that clearly, the search doesn't end. It just becomes quieter. We'll rest there, just for a moment, and then keep going. You don't have to understand all the answers to feel the shape of the question. You don't have to measure the universe to feel the distance. You don't have to solve for time to feel it passing. Right now, wherever you are, space surrounds you, quietly, without edge, without center. You're sitting, or lying, or listening, inside something vast, not separate from it, not outside it, inside. And even if it goes on forever, that forever includes you. It's easy to imagine the infinite as cold or unreachable, but it's not always like that. Sometimes it's small, local, tucked into ordinary things, the curve of a hand, the path of a thought, the number of moments between now and tomorrow. You've been holding infinity this whole time without needing to stretch. So now, if your eyes are heavy, or your mind is still, or your breath has slowed, you can rest. The universe won't end when you stop thinking about it. It will keep expanding, or not. It will continue to surprise, to recede, to unfold. The questions will wait. And if you dream, and maybe you will, you might drift not away from the stars, but deeper into them. Not toward the edge of something, but into the middle of everything. A place that doesn't need a border to feel complete. A quiet near the edge of infinity. We'll see you again, whenever you're ready.